Today we're still going to talk about Hamiltonian circuits, and a Hamiltonian circuit again is where we go to every vertex just once and then we want to return back home. One of the most common problems in this is something that's called the traveling salesman problem. In the traveling salesman problem, what we want to do is have our salesman be able to go to every city that he needs to go to and get himself back home, and he wants to do it as cheaply as possible, whether we're thinking about mileage and try to be efficient that way, or whether we're thinking about like costs of plane or trains and be efficient that way. We are going to learn two what are called algorithms, which is like, that means step-by-step process of finding cheap routes. Neither one is guaranteed to actually find the best route. So they are guaranteed to find decent routes, but neither one will actually always be the best way to do it. The only way to guarantee that you've actually found the best way is to do what we called in the last lesson brute force, and find every single possibility and then figure out the shortest from that list. That can be a very lengthy process to do. So to actually find the best route can be a bit painful, especially once we get into graphs that are this large. If our graph only has 4 cities, 4 vertices, then it's not as bad to find all the different possibilities from a certain point. But once we start to add a lot of vertices to it, it becomes quite complicated. These algorithms only work on what are called complete graphs. We defined that a few days back. What does complete graph mean?
Ones that are like finished?
Every connection that can be made is made. Okay? So that means in these, every city has to be connected to every single city. Okay? Every point has to be connected to every point. So the first algorithm is called the nearest neighbor. And it says start at the designated vertex, or if one isn't specified, you just pick a point. Okay? I think in the homework I specified that you have to begin at point A. So you start at one point. Then it says choose the route with the lowest weight. Then from there, choose the next nearest neighbor only from the vertices that haven't yet been visited. You don't want to go back home yet. Do that until all of the vertices have been used, and then return to the start. So in the left-hand one here, we're going to do this nearest neighbor. So we're going to start at A. And then we want to choose the cheapest place to go from A. So A to B is worth 8, A to C is 15, A to D is 4, A to E is 7, 5, sorry. Sometimes it's kind of tricky to tell which one is which. I tried to move them out, but this 5 is what applies to that one. And then A to F is 13. So 4 is our cheapest route, so that's the one we're going to take.
Wait, what were we trying to get?
Okay. We will want to go to every point. We're going to find this Hamiltonian root again, where we want to go to every single point before returning back to A, but we're trying to do it as cheaply as possible. And the nearest neighbor algorithm says start at A and then go the shortest route. So this one has a length of 4, or a weight of 4, a cost of 4. So we're going to choose that one because that's smaller than any of the others. Now from D, I want to choose the lowest one, but I don't want to go back to A. So even if that was the lowest one, I wouldn't want that one. I want the next lowest one. So A to B is 2, A to C is 12, or D. D to F is 7, and D to E is 8. So 2 is our next cheapest one that we can go. That takes us to B. Now from B, I don't want to go back to A because I already went there. So I could go to F, and that one has 5. I could go to E, and that one has 11, or I could go to C, and that one has 6. I want the cheapest one, so I want 5. Now from F, I don't want to go to A, I don't want to go to B. I could go to C, and that one is 14. I could I don't want to go to D, so I could go to E, and that one is 10. So 10 is our best option there. The only place that I haven't been yet is C. So I have to go to C no matter the cost. And then I have to close this thing up no matter the cost. So I have to go back to A. Then what we would do is look at how much each of these cost us and add it up, and that gives us our total. So first one was 4, and then we did 2, 5, 10, 6, and 15. We would add that all up.
That's it.
And find that this trip cost 42. Finance?
So are you just giving it to us in like the plain mentality, but really it's just like you're just trying to find it? Show this.
Yeah, most often in real life and actually applying this, that's what it applies to, is trying to make a cheap trip.
Okay.
But that's, just one example. There could be other ways, other things that these numbers mean. And we have another example of that. All right, so that's the nearest neighbor. So nearest neighbor, start at a point and go to the closest place from that point each time until you start to run out of options, and then close it up. The other one is the best edge, and it says choose the edge of the smallest weight overall. Then mark the next smallest edge as long as it doesn't complete a circuit. So we have to make sure we're not making any triangles or squares or anything like that. We don't want to complete a circuit. And it doesn't add a third edge to a single vertex. Because in a Hamiltonian, I should be able to like take that purple graph that I did and unfold it all so that it really just makes one big circle. Right? We call that isomorphic when we start moving them around. I should be able to rearrange that so it's really just kind of a circle. All right? So our best edge says we're going to pick our smallest one, pick the next smallest one, as long as it doesn't close it up and it doesn't add a third edge, because I can't have a third edge if I'm really just trying to make a circle. Right? And we keep on doing that until we get pretty limited, and then we have to close it on up. So we're going to do that now from this other one. When it tells you to do best edge, it doesn't matter what letter you start with, because in the end, as we write out our cycle, we'll just make sure we start at that letter. So the best edge in the whole picture has a weight of what? 2.
So you just by looking the lowest weight.
Yep, just grabbing the lowest weight from anywhere in the picture. So 2 is the best we can do. Then we want to take the next best. And if there's multiples that have the same, you just pick one. It doesn't matter which one. So if there's ties, you take whatever one you want. So what one is the next best? 4.
Are we supposed to be adding these up as we go?
You could add them up as you go, or you can just wait and add them all up at the end.
Wait. And you're just trying to hit every point by the lowest. It'll always work.
In the end, we need to make sure that we've hit every point, and just once. All right, so then I need to pick the next lowest. So what's the next lowest? 5. And there are actually 2 options that have 5, so I can just take either one of them. I'll start by taking the BF one. That didn't close up any circuits, and it didn't add a third edge, so that's good. The more we start to add in here, we really need to be careful that we're not closing up a circuit or adding a third edge to a vertex. So then I can try now taking the other 5 and see if that one works as well. And that 5 goes from A to E. So that one seems to work as well. I didn't close up any circuits still. So then what's the next best? 6. Okay, well I've got 1 6 that goes from B to C, but I can't use that one because that would add a third to B. So we can't do that. I've got another 6 that goes E to C. So I can do that one. That didn't close anything up, and it didn't add any third edges. That was worth 6. And so far, we've drawn in 1, 2, 3, 4, 5 of them. In the end, if there's 6 of them, we should have 6 of them, so we really only have 1 more to do, which means we have to just close this up no matter the cost. So closing it up no matter the cost gives us a cost of 14. So a lot of times in the best edge algorithm, your last one ends up being pretty heavy because you don't have a choice about it. You just kind of get stuck with it. And so we add that up, and we got 38 on this one. Best edge is not always better than nearest neighbor. Okay? Neither one is guaranteed to be better than the other one, and neither one is guaranteed to be the actual best. There might be some other that actually is a better one that is not one of these. Now, if you are asked to give the root, you would just name off the letters. Sometimes it'll say starting at a particular letter. So we didn't care about that in the beginning, but now we could really start this thing anywhere. So if it said starting at A, name the root, I could go A, and I can go either way of what's being connected to A. So I could do A, D, B, F, C, E, A would be a way to name this root. So I just start at one point, and then just follow my paths until I get myself back home. All right. Questions? All right, so then we have another example here. It's a little bit different of an application. So it says a tool maker needs to use one machine to create 4 different tools, and the machine needs different setups before starting each tool. But some parts are in common, so sometimes changing from one tool to another is easier. So this chart shows the estimated time in minutes that it would take to adjust the machine. And so what we need to do is figure out how long would it have to take him to make all 4 of these machines in a given day. So we could create a graph of them. So A to B is 25, A to C is 6, A to D is 32. B and A are already connected, but B and C is 18, B and D is 9, and C and D is 15. And that completes out our graph. So it says now that we want to use each of the algorithms to determine a good sequence for him to make the tools. It says the machine is currently configured for tool A and should be returned to that state at the end of the day so that he's ready to start again this next day. All right, so if we do the nearest neighbor. For nearest neighbor, I'm going to start at A, and where am I going to go from A? What is closest to A?
D. Yeah, distance or like number?
Number. C.
Oh.
That has a weight of 6, so that's our shortest route. So I'm going to go A to C, which is worth 6. And then from C, where can I go the most cheaply? D. And that's worth 15. And then I can't go back to A or C, so all I have to do is go to B because that's it. That's the only thing I have left to make. So I have to go to B no matter the cost, and the cost is 9. And then I've got to get myself back to A, and B to A is 25. So we add that up, and we get 55 for our nearest neighbor.
Wait, nearest neighbor, like, why didn't you go to 9 instead of 15? Is that because it didn't connect? No.
Yes.
Yes.
Yeah, nearest neighbor, we're making connections, starting at one point making connections. Best edge is where we just start to get to pick all the best numbers we can pick. So for best edge, to draw out the graph again, in best edge, we get to just pick our best edges. So best edge, what is the best edge?
6.
6. What's the next best edge? 9. What's the next best that either doesn't give me a third to a point or close us up? 15. And then what's our next best? Well, we have to close it up at this point because we've hit all 4 points, so we don't really get to pick a best, we have to pick the 25. This ended up being exactly the same thing. So we got 55. The smaller the graph, the more likely that is that that's going to happen. I mean, if you got 3 points, it's a triangle. So it doesn't matter what algorithm you use, that's it. That's your choice, is the 3 sides. Once we add in one more, we do start to have some options, but it's more likely you're going to keep on ending up with the same answer. Once we start adding in 5 or 6 or more points, then it's not as likely that these roots are going to end up being exactly the same. But here in a small graph, they're going to end up being the same a lot. Questions?
I have no homework.